Alright guys, so here's video 2. The first problem we're going to look at today is about refraction and Snell's law. Refraction is when light gets bent when it changes mediums. And if the light goes from a higher index of refraction medium to a lower index of refraction medium, it's going to bend away from the normal line. If it goes from a medium with a lower index of refraction to a higher index of refraction, it's going to bend toward the normal line. For example, here we have light leaving air and going into water. This is the angle of incidence. As the light enters the water, notice that it bends toward the normal line, and the angle of refraction, that one, is smaller than the angle of incidence. There's a relationship between these two things called Snell's law. And you can see it down at the bottom of the screen, but essentially, Snell's law looks like this. The sine of the angle of incidence times the index of refraction of your beginning medium is going to be equal to the sine of the angle of refraction times the index of refraction of your ending medium. So let's look at how a problem might look for this. So notice what we've got there. A beam of light in air is incident upon a piece of glass, striking the surface at an angle of 30 degrees. If the index of refraction is 1.5, what are the angles of reflection and angles of refraction? All right, we're going to call the index of refraction for light in air, we're going to call that essentially 1. First part of the question, though, what's the angle of reflection? If you remember the law of reflection, it says that the law of the angle of incidence is always equal to the angle of reflection. So if our angle of incidence is 30, our angle of reflection is 30. That takes care of this. Some of the light will be reflected, some of it will go on into the water and it'll be refracted. To find that angle of refraction, we're going to have to use Snell's law, which is right here. So let's start with the air side of this equation. Like we said before, the index of refraction of air is 1, near 1. The angle of incidence in this problem is 30 degrees, so sine of 30. That's going to be equal to the index of refraction of the glass that we're entering into, which is 1.5, times the sine of the angle of refraction. So we have to solve that out for the angle of refraction. We're going to divide both sides by 1.5. Cancel that out over here. So let's go the sine of 30, which is a half, times 1, divided by 1.5. And then to solve for the angle of refraction, we need to take the inverse sine of both sides. And when we do, we get an angle of refraction of 19.5 degrees. And remember, that angle is the angle between the normal line and the refracted ray of light. The other part of the problem we need to look at is the bottom part. What's the speed of light in glass? This right here is an important relationship to remember. That the index of refraction is the ratio of the speed of light in a vacuum to the speed of light in the medium. Well, we know the index of refraction of glass is 1.5. It's given to us in the problem. Hopefully you know that the speed of light in a vacuum is 3 times 10 to the 8th meters per second. So let's take this equation and solve it out for V. If we rearrange it a little bit, we're going to get V equal to C over N. And then let's go down here and just solve it out. So the speed of light in glass is going to be equal to the speed of light in a vacuum, 3 times 10 to the 8th meters per second, divided by the index of refraction of the glass, which is 1.5. When we do the math on that, we get a speed in glass of 2 times 10 to the 8th meters per second. So the light slows down quite a bit when it moves from air into light, and that's why it refracts. All right, that's problem number 1. We will move on in a second and do problem 2. All right, guys, so the second kind of problem we're going to do on this video is looking at the energy level diagram for an atom. We're looking at hydrogen here. Remember that when we add energy to an atom, whether it's through heat or light, that electrons tend to move up. They move away from the ground state. They move to excited states. But to get back down, they have to release energy. So to figure out how much energy that they're going to release, we're going to take the energy at the level that they're at. Let's say we have an electron at level 6, and let's say that it drops down all the way to the ground state. If we want to know how much energy is released, we're going to take the initial energy minus final energy. So in this particular problem, we're going to take negative 0.38. That's where that electron is starting at in its excited state. And we're going to subtract from that the energy at the ground state. So that's going to be minus 13.6. So if we do the math on that, negative 0.38, it's going to end up being plus 13.6, minus. So we end up with 13.22. And this diagram is usually in terms of electron volts, which is a very small amount of energy. But that's the amount of energy that would be released when this electron dropped from level 6 all the way down to the ground state, level 1. Let's look at one other problem related to this. So here's some information to know. Let's say that instead of doing that, let's say that we looked at an electron that dropped from, say, level 2 down to level 1. So at level 2, we've got negative 3.40, and at level 1, 13.6. So at first, we want to know how much energy is released as this electron drops from level 2 down to the ground state. Remember, at level 2, our energy is negative 3.4 electron volts. And at level 1, it's 13.6. I think it's 13.6. So the first thing we want to do is define the energy. So to find the energy, we're going to say that the energy released is equal to where we started, negative 3.4, minus where we ended up, 13.6. Subtract that out. Yes, 10.2 electron volts. That's the energy that's released. And when we're doing the problems like this, we probably want to convert that directly over to joules, because electron volts we don't use a whole lot for in math. So this relationship right here is on your AP Physics formula sheet. Let's go ahead and convert it out.
What number is that also? It's also a number for involving an electron.
It looks a little bit like the mass, but it's not. It's not the mass. Cancel out those electron volts. So essentially, we're going to go 10.2 times 1.6 times 10 to the negative 19. And we end up with 1.63 times 10 to the negative 18 joules of energy released. Now the next thing you might want to know is what kind of light are we releasing? What's the frequency of the light? What's the wavelength of the light? That's when we're going to go to this equation, E equals HF. This is the energy of a photon, which we just calculated, 1.63 times 10 to the minus 18. H is Planck's constant, which we've got right here. We're going to try to find the frequency. So the frequency of our light is going to be equal to energy of the photon divided by Planck's constant. Here's the energy of our photon. I'll put that right there. And I'm going to go ahead and round Planck's constant to 6.63 times 10 to the minus 34. And those units can be written as joules times seconds. So let's divide this out. And again, it's going to be 1.63 times 10 to the minus 18 divided by 6.63 times 10 to the minus 34. And of 4 disappeared. That's supposed to be a 4 there. So when we divide that out, we get a frequency of 2.46 times 10 to the 15. It's going to be over seconds, which is hertz. That's the frequency of our light. One other thing they might ask is to find the wavelength. This is a really important equation. C equals lambda F. We're trying to find a wavelength, which means lambda would equal C over F, where this is F, and where C is the speed of light in a vacuum, 3 times 10 to the 8. If we want to find the wavelength in this problem, let's take 3 times 10 to the 8th and divide it by our frequency that we just calculated, 2.46 times 10 to the 15th. When we do that, we get a wavelength of 1.22 times 10 to the minus 7. If we do everything in terms of hertz and meters and seconds and joules, our wavelength is always going to come out in meters. So we calculated 3 things there. We calculated the energy that was released. First we did that in electron volts. We converted it over to joules. Then we used the equation E equals HF. The energy of a photon is equal to Planck's constant times frequency. We solved that for F. We plugged in the energy that we calculated right here. We plugged in Planck's constant right here. We got a frequency. We then used the equation speed of light in a vacuum equals wavelength times frequency. Solve for wavelength. Put in the speed of light in a vacuum. Put in the frequency that we calculated earlier. And we came up with a wavelength of 1.22 times 10 to the minus 7. All right, the other thing that I want to talk about from this particular presentation has to do with radiation. And I want us to make sure that we can fill out nuclear equations. So let's just go through these problems. Here we have radium-226. Remember that this bottom number down here is the atomic number. It's the number of protons. This top number is the mass number. It's the number of protons plus the number of neutrons. Regardless, both of these numbers on the left have to be the sum of all the mass numbers and all the atomic numbers on the right. So what we're looking at here, this is an alpha particle, alpha decay. It's 4 and 2, which means over here, since this number over here is 226, this has to be 222. This number right here, 2. This number here, 88. So the atomic number over here has to be 86. Then we look at the periodic table, which I don't have handy right this second, and we find what element 86 is. Pause this for a second. We take a time out for a second and get a periodic table. All right, let's try this again. So back to what I was saying. We got our alpha particle. The mass number over here has to be 222. The atomic number has to be 86. Element 86 in your periodic table is radon. This is radon gas. So this is an equation for the alpha decay of radium-226. It's shooting out an alpha particle, which is the nucleus of a helium atom. Moving on down a little bit. Here we've got potassium-37. This is the symbol for what we call a positron. This is a positron emission equation. Positron is essentially a particle that's the same size as an electron, but having a positive charge instead of a negative charge. The equations work the same way. The numbers have to add up on both sides. So since this is 37 and this is 0, mass number over here has to be 37. This is 19, this is plus 1, this has to be 18. We look at our periodic table, find element 18, and that's an argon. So again, that's a positron emission type of reaction. Down here, we've got Neptunium-239. It's decaying into plutonium-239. Notice the mass numbers are the same, which means this particle has to be 0. Notice this is 93 and this is 94, which means that has to be -1. Whenever you get a -1 charge, that's going to be a beta particle, which we could write as beta. Or we could just put an E there, because a beta particle is essentially just an electron being shot out at a really high speed. It's when a neutron over here in Neptunium broke apart and shot out its electron, and essentially what was left was an extra proton. But again, that's beta decay. Down here we have what's called a fusion reaction. We're taking two small atoms and actually combining them together to make one bigger atom. And all you do here is just add up the numbers. So we've got 1 plus 3 to give us 4, and then 1 plus 1 down here to give us 2. You look in your periodic table, that's helium, and that's a fusion reaction. That's the kind of thing that happens in the sun and in stars. Down here on the bottom, we've got 27 and 4. That's 31. Here we only have 30, which means this number has to be a 1. Here we have 13 and 2. It's 15. Here we have 15, which means this has to be 0. If you ever see that particle, 1 and a 0 on the bottom, that is a neutron. So as this decay process happens, this atom is shooting out a neutron, probably at high speed. Down here we have 241 and 4, so 245. This is shooting out 2 neutrons, so that's 2, which means this has to be 243. 243 plus the 2 from the neutrons. Here we have 97 on this side, 95 plus 2. We've got 0 down here, which means this has to be 97. We look up element 97 in our periodic table, and that is the element berkelium. Berkelium or berkelium. Yep. So now let's finish this one up. And number 7 is maybe one of the most important reactions that we've ever figured out how to do. I think our mass number on here is maybe a little off from what it really should be, but let's just make the equation work the way it is. We've got 3 on top, plus 91, that's 94, plus 142. So we're adding 142 plus 94 to get 236. And notice we're adding a neutron here, which means this is actually going to be 235. So actually we're good here. Down on the bottom, we got 0, 36, 56. That's going to give us 92. And if you look in the periodic table, element number 92 is uranium. This is actually one of the first recorded fission reactions. We're shooting a neutron into the nucleus of a big atom like uranium or plutonium, and essentially playing pool to some extent with it, breaking that nucleus apart. These are going to cause that to happen over and over again, and eventually going to start a chain reaction. But this is the kind of reaction that powers nuclear reactors, nuclear bombs. All right, hope that helps. Stop there.